7 visitors approach Earth, a title that sounds incredible, but it is reality. By the end of 2025, 7 major comets will converge in the inner solar system within just 6 months, creating a stream so rare that leading research projects like Pan-STARRS and ATLAS have never recorded anything like it. Among them is the comet Tri-I/Atlas, only the third interstellar comet ever discovered. Its exotic chemistry and vast green coma make it a true cosmic wildcard. The chance of this occurring by coincidence is less than 0.5% per decade. Is this merely an astronomical coincidence? Or are we witnessing something that defies the rules of our sky? Answers and risks begin here. Every night, a silent network of digital eyes scans the firmament. These automated hunters of comets, Pan-STARRS, Atlas, and their kin, installed on the remote mountains of Hawaii, Chile, and South Africa. These telescopes cover almost the entire sky, night after night, capturing faint glimmers that would escape the most attentive observer. Their cameras are sensitive enough to detect objects with a brightness of up to 21 stars, much dimmer than Pluto when seen from Earth. Each image is a mosaic of millions of stars and galaxies, but the true reward is the movement, a single pixel drifting from frame to frame, revealing the presence of a new comet. The process is relentless. Pan-STARRS and Atlas operate on a schedule that covers much of the sky every 2 to 3 nights. Their software compares each new image with the digital memory of space, noting everything that has shifted. As soon as a new candidate appears, a chain reaction begins. Automatic notifications, rapid following of telescopes around the world, and a race to confirm the discovery before it fades into the background. This digital vigilance has changed the game. 20 years ago, the discovery of comets required months of patient skywatching and a bit of luck. Now the number of finds doubles almost every year. Faint distant visitors that once eluded attention are now spotted, cataloged, and analyzed in real time. The Center for Small Planets records every discovery, creating an inventory of icy wanderers that grows by the hundreds. Yet, despite all this power, even the best studies rarely capture more than a couple of bright comets in a single season. The concentration of 7 significant comets at the end of 2025 exceeds the limits for which these systems were designed. Engineers and operators, usually content to let the algorithms run, are now glued to their screens, watching as the data stream fills with notifications of comets no one expected. For the first time, machines cannot keep up with the sky. Before delving into this celestial congestion, it is helpful to have a brief guide at hand. Scientific terms related to comets have their nuances, but most are simpler than they seem. Perihelion is simply the closest approach of a comet to the sun, the point where sunlight does its work, transforming the frozen core into a spectacle of gas and dust. The word often appears in comet forecasts for a reason. This is the moment when the action begins. Distances in the solar system quickly become vast, so astronomers use the astronomical unit or astronomical unit of distance as a shorthand. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles or 150 million kilometers. If a comet's perihelion is 0.25 astronomical units, it means it is a quarter of the way from the Sun to Earth. For skywatchers, the closer the comet, the higher the chances of witnessing a bright spectacle. When talking about brightness, astronomers use a scale of stellar magnitude, where lower numbers indicate brighter objects. A star magnitude of 6 is the faintest that most people can see without optical instruments in a dark sky. But a magnitude of 3 or 2? That's bright enough to catch the attention of anyone stepping outside at dawn or dusk. Some comets, with a bit of luck, can even outshine the brightest stars. Now let's talk about tails. Each comet, as it approaches the sun, forms at least 1 tail, sometimes even 2. The dust tail is wide and pale, made up of tiny particles pushed away by sunlight. The ion tail is straight and blue, formed by charged gases that are carried away by the solar wind. It can be imagined as a flag for space weather. Sometimes a solar storm can tear this tail away, but it quickly regenerates in a matter of hours. Such events as tail disconnections are rare, but with so many comets filling the inner solar system, the year 2025 may gift several such moments lived. Remember these basics. They will help you decipher every news, every sky map, and every surprise prepared by the 7 visitors. Statisticians working with comet data sometimes joke that the universe is stingy with surprises. During a typical 6-month period, one can expect 2 or maybe 3 comets bright enough to be observed through a backyard telescope. The others will be dim, distant, and meant for the archives of the Center for Small Planets. But at the end of 2025, these expectations will be disproven. 7 significant comets, each with a perihelion, gathered in 1/2 year, caused alarm in every Monte Carlo model run by comet population modelers. The numbers are impressive. Over the past decade, digital research has elevated the detection of faint comets to new heights. However, even with the best technologies, simulations show that a cluster of 7 comets in one season is a statistical exception. When researchers input real data about the sensitivity of observations and population estimates of comets into their models, the median expectation is only 2 or 3 comets over a 6-month period. The probability of 7 comets appearing? Less than 0.5%. Some simulations give odds closer to 1 in 1,000 years for a group of such brightness. This rarity is not merely a result of improved cameras or more vigilant software. Bright comets obey the laws of their orbits and the randomness of when they are pushed towards the sun. The effectiveness of observations may find more dim wanderers, but cannot create a group of 7 large visitors. The composition of cosmic objects expected in the year 2025 stands out against all records of the digital age, and even old photo documents can hardly find similar events. For data scientists, this is an anomaly requiring closer analysis. Is this the consequence of a distant collision, or a random manifestation of unusual cloud dynamics? Or perhaps it's just a cosmic coincidence so rare that it seems scripted. In any case, the facts speak for themselves. The cometary congestion of the year 2025 is perhaps the closest case to winning the celestial lottery that modern astronomy has ever observed. Some comets slip through the solar system almost unnoticed, their dim glow lost against the stars. Among the 7 visitors of the year 2025, 2 belong to this inconspicuous category: C222102 and 240P20. The Pan-STARRS comet reaches perihelion on July 31st, passing approximately 3.82 astronomical units from the Sun, significantly farther than Mars, closer to Jupiter's orbit. At such a distance, sunlight barely touches the icy surface of the comet, resulting in a modest coma visible only through telescopes with sensitive detectors. Most observers from their backyards won't be able to see more than a dim spot, even on the clearest nights. 240P20, another returning traveler, will pass by December 12th at a distance of 2.12 astronomical units. It is still twice as far from the Sun as Earth, affecting its brightness. This comet has made similar journeys before, each time offering a modest repeat for those willing to watch it in the winter sky. The main audience for both objects is a dedicated group of astronomy enthusiasts, documenting observations, compiling images, and sharing notes online. Their patience fills in the sparse data on comets, ensuring that even the quietest visitors are accounted for. Although these 2 comets will not be the center of attention, they remind us of the full spectrum of participants from the 12th year, from quiet observations to spectacular revelations. Their presence creates a backdrop for the brighter and more dramatic objects yet to be seen. For those who have ever stepped outside and dreamed of a comet bright as stars, the end of the year 2025 offers much more than just a faint hope. 3 of the 7 visitors, Swan, Atlas K1, and Lemon, promise to be true spectacles, each bringing their share of impressions. The Swan, officially known as C2020R2, will approach Earth on October 21st, passing just a quarter of an astronomical unit away, which is about 37 million kilometers. It is close enough for the solar wind to create an impressive tail, and bright enough for even casual observers to notice it at dawn with the naked eye. Mission models predict that Swan may reach 2nd or 3rd magnitude, turning the comet observation into an event for the entire area. In just a few weeks, on October 8th, Atlas K1 will rapidly approach its perihelion inside Mercury's orbit at a distance of 0.33 astronomical units. Intense sunlight at this distance likely activates the comet, launching powerful jets of gas and dust. Astronomers closely monitor the growing tail and unpredictable bursts that create stunning headlines. At this time, the Lemon Comet, designated C2025A6, approaches and will make its closest pass on November 8th at a distance of just over half an astronomical unit from the Sun. Forecasts suggest it may shine to 4th magnitude, possibly even 3.5, making it visible at sunset in the northern hemisphere, and an excellent object for backyard binocular observations. Each of these comets has its unique energy. The close passage of the Swan Comet, the fireworks of the inner orbit of the Atlas K1 comet, and the classic evening show of the Lemon Comet provide a chance to see something rare, a comet so bright that no telescope is needed for observation. However, not all comets on the 2025 list are best observed from Earth. Some, like the 14th comet P-Stereo, are practically invisible to backyard telescopes, but are the focus of the fleet of spacecraft operating around the Sun. On September 27th, the 14th comet will pass slightly more than half an astronomical unit from the Sun, closer than Venus, but its orbit hides it in sunlight from our perspective. Here, missions like SOHO and STEREO come to help. Their cameras, designed to monitor solar storms, capture comets as bright streaks in the solar corona, revealing details of activity that observers on Earth cannot detect. Team groups at NASA and ESA are already working on the schedule, weighing which comets will receive precious observation time with instruments. October's sky will be busy, not only with comets but also with scientific priorities. The comets Swan and Atlas K1 promise spectacular tail displays, while the three-eye burst Atlas, an interstellar newcomer, demands close attention during its brief passage. Each spacecraft has a limited field of view and can only target one object at a time. This means a difficult choice: to focus on the rare interstellar chemistry of Tri-Drub Atlas, or to observe the changing tails of Cygnus and Atlas K1, which react to solar storms. Heliospheric images and coronagraphs will track the events of the tail disconnection in real time, capturing the moment when a solar eruption tears the comet's tail. These observations are not just indicative. They show how the Sun's magnetic field shapes comet tails and, consequently, the invisible space weather filling our solar system. In 2025, spacecraft and ground telescopes form a coordinated network, each covering angles that others cannot reach, ensuring that no visitor goes unnoticed. 7 comets arrive within one calendar period. From late July to December, the inner solar system becomes a cosmic highway. The first visitor, Pan-STARRS, makes its distant pass in July, barely triggering the detectors. Then the pace quickens. By September, the Swan approaches, followed by the 14th Comet P-fragment STEREO slipping past the Sun, while spacecraft strive to take the best positions. October becomes truly crowded. Atlas K1 is rapidly moving towards the Sun, actively emitting gases within Mercury's orbit. Just a few days later, the comet Tri-Eye Atlas, an interstellar outsider, pierces a hyperbolic trajectory past Mars. Its coma expands to hundreds of thousands of kilometers in diameter. In November, the Lemon Comet follows her, slowly sinking into the evening sky with a promise of brightness visible to the naked eye. Finally, in December, the Comet 240 PO NEAT concludes the sequence, a quiet ending for those still watching. On the timeline, these appearances do not look like a random distribution, but rather like a cosmic signal. The perihelions of each comet occur in weeks close to each other, leaving astronomers and sky enthusiasts little time to rest. A compressed schedule implies overlapping observational campaigns, loaded data channels, and a constant flow of new images. For the first time, the task is not to find a comet, but to remember which one you see. These 6 months of compression turn the sky into a living laboratory, where the mechanics of comets, tails, and solar winds unfold in real time. Sometimes, several comets can be seen in one frame. The scene is ready for the season of tail physics and unparalleled solar drama. Each comet on the list for the year 2025 brings its unique feature to the night sky, but nothing stands out like the double tails that follow them. The difference lies in what is expelled and who does it. The dust tail is wide and curved, made of microscopic particles blown off the surface of the comet by the force of sunlight. These tiny particles scatter sunlight in all directions, giving the dust tail a pale, sometimes golden glow that can stretch for millions of kilometers. It smoothly disperses behind the comet, following the curve of its orbit like a glowing trail. The ion tail, on the contrary, is a straight, narrow band of electric blue color. This tail forms when ultraviolet light from the Sun strips electrons from gas molecules in the coma, turning them into ions. The solar wind, a stream of charged particles rushing from the Sun, captures these ions and hurls them away, regardless of the comet's direction. As a result, there is a tail that always points directly from the comet to the opposite side of the Sun, often with a sharper edge and brighter color than the dust tail. For skywatchers, the visual cues are clear. Dust tails are wide, soft, and often yellowish or white. Ion tails are thin, straight, and blue. Each tail tells its own story of the acting forces, and both are influenced by the mood of the Sun. When a solar storm engulfs space, the ion tail can be severed in an instant, demonstrating how dynamic and unpredictable these cosmic visitors can be. Solar storms not only illuminate the auroras, but can also turn the elegant tail of a comet into a battlefield. When a powerful coronal mass ejection, CME, sweeps through the inner solar system, it carries the Sun's magnetic field with it. If a comet is caught in the impact zone, The results can be spectacular. The ion tail, this straight blue wedge directed away from the sun, can be severed in just a few minutes. It is not a gradual disappearance or slow unraveling. At one moment, the tail stretches for millions of kilometers, and the next, it is severed, drifting in space while the comet forms a new one. The most famous case occurred in April 2007 when NASA's Stereo spacecraft captured the moment of Encke's comet disaster. A coronal mass ejection struck the ion tail of Encke, severing it in real time. These images became examples for study, shown at heliophysics seminars and comet observer forums. Scientists call such events magnetic reconnection, a sudden reconfiguration of magnetic field lines that ejects ions from their position. For several hours, the comet remains unprotected. Its tail becomes a visual indicator of the invisible force of the sun. At the end of 2025, when 7 comets will be on the ecliptic, the chances of capturing another moment of tail shedding will be higher than ever. Heliophysicists and astronomy enthusiasts are on alert, watching for signs, a sharp bend, a rupture, or a ghostly trail left behind. Each such event offers a chance to see how far the sun's influence extends. A reminder that space weather is not just a theory, but what is written in the sky in real time. Comet tails not only create beautiful images, they also serve as instant reports on space weather. The reason? Geometry.